we're going to be studying in this chapter, chapter 20, the very last chapter in the book, nuclear chemistry. And this chapter is going to be quite a bit different, but let me pause for a few seconds to let you turn off the video and copy down these notes. Okay, so up till now in chemistry, we have been talking about the activity of the electrons. Chemistry mainly involves electrons, especially those valence electrons, the very outermost electrons that are most reactive that we have talked about. However, when we talk about nuclear chemistry, we're actually going to be focusing on the nucleus, and there are some reactions that can take place in the nucleus. And in fact, when you hear nuclear chemistry, there are probably some things that you think of. You probably think of the atomic bomb. You think of warfare, nuclear warheads, and possibly other bad things like that. You might think of radiation sickness. You might think of nuclear power plants, which, if they're managed well, are actually very clean energy. But if they get out of hand and get out of control, they can be very detrimental. Also, one thing you may or may not think of is medicine, nuclear medicine that's used to treat especially cancer. So, like anything in chemistry or really anything else in science, nuclear chemistry can be applied for good things or it can be applied to bad things because we do live in a fallen world. So, also, sometimes you may think that all of this is more man-made. You might think of nuclear reactors and things like that. But we're going to take a look at, in section 20A, natural radioactivity. This is something that occurs naturally, that occurs in nature, and was first discovered in that manner. And so, some terminology we need to be aware of as we're studying this. Nuclear chemistry is the study of radioactivity, the nucleus, and the changes the nucleus undergoes. So our focus is shifting from electrons to the nucleus. And a nuclear reaction is a reaction that takes place within the nucleus of an atom, as we discover this. So before we completely jump into this topic, let's talk a little bit about the history. So I'll give you a couple of seconds to turn off your video and copy this down. Okay, so the discovery of radiation. It was first discovered by Henri Becquerel, a Frenchman. He was studying uranium compounds and he discovered that they released rays that exposed photographic film. He did not realize where the energy for this was coming from at the time. He thought that it was because they were compounds, because he was looking at these uranium compounds. He thought it was something chemical to do with their bonding. It was, in fact, the Curies, Pierre and Marie Curie, who coined the term radioactivity. This is the spontaneous emission of penetrating rays from the nuclei of atoms. They are the ones, even though Becquerel discovered that radiation existed, they are the ones who discovered where it came from. And I'm sure you have heard of Madame Curie before. Her and her husband discovered polonium, which is radioactive. And in fact, Madame Curie died from radiation exposure, from studying these compounds. Today, we know the dangers of these compounds, so we take more precautions. But when they were first studying these, they did not know the dangers. Now, when we talk about radioactivity, we'll be talking about radioisotopes. This is any radioactive isotope of an element. In some cases, all isotopes are radioactive. Remember, isotopes have the same number of protons, different numbers of neutrons, so they have different masses. And in some cases, like in carbon, just one isotope is radioactive. and the others are not. So it can be a mixture of both, where all isotopes are radioactive or just certain ones. Okay, so moving on, it has since been discovered that there are 3 different components to radiation. And so here they are. They're in different sections, but I will show you these and pause for a few seconds so you can stop your video and copy these down. Okay, so let me quickly talk about these components. And I say components because 2 of them are particles and 1 is energy. So the components are alpha particles, beta particles, and gamma rays. So if we take a look at the alpha particles, this is the symbol for an alpha particle. This is the notation we're going to use when we write nuclear reactions later on. So an alpha particle is the nucleus of the helium atom. It's 2 protons and 2 neutrons. That's why the notation is helium for the mass and 2 for the charge. And sometimes it's also represented by He2 positive, so helium with a 2 positive charge, or H4 2 positive. So this would show the mass with the charge. So alpha particles have a positive 2 charge. They are the most massive of the particles because they have a mass of 4. They are positively charged. They discovered that they are positively charged because they deflect toward a negatively charged plate. They also know that it's the most massive because due to inertia, when they go towards the positively charged plate, their path does not change as quickly as if they were less massive. So that's one way they knew that they were more massive at first, is because of inertia and that momentum keeping them more on a straighter path and not curving as quickly. And they have the greatest ionizing power. That means they are the least penetrating. They are actually the least harmful to people. In fact, alpha particles can be stopped by this sheet of paper. They will not pass through the sheet of paper that you are writing on. However, they still can cause damage to an individual if they are exposed to enough alpha particle radiation. For example, they think that the Hiroshima bomb and the Nagasaki bombs, a lot of the radiation burns were caused by alpha particles. So they can burn you if you're exposed to enough. The second particle is the beta particle. So we have our Greek letters. And the notation we'll use when we write our reactions is this, with a -1 charge and 0 mass. So this is essentially an electron that has been formed in and emitted from a nucleus. They have very little mass, hence the 0 charge, as we know that electrons, just regular electrons that are outside the nucleus, also have very little mass and don't really contribute to the mass of the atom. They know that they're negatively charged because they're deflected toward a positively charged plate. And they deflect much more quickly than the alpha particles because they have very little mass, they have very little inertia. They have medium ionizing power, so they are more penetrating and they will actually cause more damage to an individual because they will actually go into your skin. Okay, alpha particles would be absorbed more by your skin. These will penetrate further, and so they will cause more damage. And the ionizing power has to do really with chemical activity. These do not combine with other elements as quickly as the alpha particles. So if it's absorbed very quickly, reacts very quickly, it doesn't penetrate very far. If it does not, it goes further. So that's the difference. Also, the other thing I wanted to say about these, where they come from is they've discovered that in the nucleus, we've talked about the 3 particles in the nucleus are the proton, which is positively charged, the neutrons, which are neutral, and the electrons, which are negative. Well, they have discovered that neutrons are made up of a proton and electron. And so when you have a beta particle that's given off, it's because a neutron is being broken down into a proton and an electron. The third component of nuclear radiation here is the gamma ray. Here is a gamma. Now, if you were to write this, I start like this and go up like that, okay? It's like this. 0 and 0 has no mass, has no charge. This is uncharged electromagnetic waves of very high frequency and short wavelength, the most harmful type of radiation. So this is not a particle like the other two. This is energy. Okay, the other two are particles. This is energy that is released. It has no mass, no charge. So this means it's undeflected in a magnetic field, and low ionizing power because it's not a particle. It is the most penetrating. This is why, well, let me say this. It can only be stopped with lead and thick concrete. So let me look this up here. I should have written this down. So several feet of concrete or a sheet of lead can stop this. This is one reason, like when you are having x-rays done, because x-rays are also high energy electromagnetic waves. Just they're actually a little bit lower energy than gamma rays. This is why when you go to the doctors and you have x-rays done, you have that lead blanket put over you, okay, over your reproductive organs, so that it will protect you from those high energy electromagnetic waves that can cause mutations. So that is the reason for that. And the reason why we don't want too many x-rays. They can be good if we need them, but we don't want to have too much exposure to that. So that is it for this section, and there is no additional homework. So get these notes down, and I'll be back with more tomorrow.